Hello everyone. Happy afternoon. Today we are very glad to invite Professor Yinyu from Stanford to give a lecture, distinguished lecture in IAS. And many of you already learned Professor Ye's career, celebrated career, one of the most distinguished mathematical optimization. And maybe you don't know Professor Ye is also a top athlete member. Actually, he keep for a while. He keep the maybe high school or college jumping record for national record in China. I think it's 1.8 meter. I never reached that. It's difficult to imagine for me. It jump beyond my height. Actually, Professor Ye has lots of contribution, and recently he received many prizes, and also his student also received lots of prizes in forms. And I guess many people here wants to be Professor Ye's student or collaborator, including myself. When I was a postdoc, I worked with Professor Ye, and that paper turns out to be my best paper ever so far. Very fond memory. Okay, maybe I should pass the control to Professor Ye.
Okay.
Thank you.
Yeah. Thank you very much for the introduction. It's a great honor for me to report some of my recent work. I'm so happy to see so many new and old friends, and Yuan, Rohan, who used to take my class, and also many other people. Even have some academic grandchildren here. So I'm doing mathematical optimization. Okay, many people talk about optimization, but I'm talking about the mathematical optimization. For any professionals at today's environment, frequent asked questions is my job endangered by ChatGPT. So here's the one I asked ChatGPT about the optimization problems. The problem is called the knapsack problems. You have a bag, okay, can only hold 5 kg weight. Then you have 5 items, the weight and the values. Now the question, which item you should put in your bag have a larger sum of values? Is that clear? Okay. So, because they only can find 5 kg, so if you think about maybe greedy algorithms, okay, now I'm just looking for the highest value, 3.5, 28, okay. I put this back in, I only have 1.5 kg left, or maybe I can put 15 in, so take these 2 items. That's the best possible way, okay? Everyone understand what I'm getting to? Okay, so then we ask ChatGPT. I never played ChatGPT, but I asked my Chinese student put these problems. Okay, put it into ChatGPT. They have several rounds of conversation, and as you know, and the ChatGPT all really make a lot of sense. Let me summarize. What they do is, ChatGPT tried to formulate the problems. So that's the formulation. Some decision variables, some objective function maximize some of the values. Then they have some constraints because they can only hold for 5G. But they also try to give an answer, but could not guarantee the correctness. That's typical GPT, okay? They're not guaranteed, okay? They cannot, promise you, because they maybe have, if they make a wrong answer, they claim this is the correct answer, they maybe have a legal consequence, so they cannot do it. And also, ChatGPT did highly recommended using reliable optimization solver and the consulting specialist. They said, I know these problems, I can formulate the problems, but if the problem is too big, I just cannot solve it. So you have to ask for some people in optimization as a specialist, okay? So in some sense, ChatGPT is like a family doctor. Then once you really have some problems, they ask you consult some surgeons or specialists to treat the problems, okay? So that's my reading about it. So at this point, I feel I'm relieved. My job is safe. Okay, I'm a specialist. I can still do research, okay? So in fact, the problem we asked ChatGPT is called linear programming, okay? So here's the formulation of the problems, like the knapsack problems. So your given data point pi j is like a reward for decision variable xj. You have many, many such decisions, xj variables. You try to maximize the sum of all these. However, an xj can be either 0 or 1 or continuous between 0 and 1, okay, for each j. Each xj, if you set xj equal to 1, you need some resources vector a sub j. So a actually is the vector. Okay? So you need some resource, but total consumed resource should be less or equal to b component-wise. You try to maximize this. This typically, in terms of mathematical optimization, this is called our objective function. These are called our constraints. And xj is the one you need to decide for all the xj should be equal to 0, or could be equal to 1, or could be some fractions between 0 and 1. Okay? That's your problem. That's your special. You need to decide. That's the linear programming. Okay? Objective functions, constraints, decision variables. 3 component, basic component for mathematical optimization. By inventing these decision models, 2 economists, okay, and also mathematicians. So this one is called Kontorovich. It's the former Soviet Union mathematicians. So this is a US economist, Krugman. They both won 1975 Nobel Prize, economic prize. Okay, the middleman is called George Dantzig. I think I probably told you some of you before. So this George Dantzig invented an algorithm, or at the time called a method, by using mathematical procedures or logic to find what's the optimal solution, what's the optimal value for each xj, which we call the optimal solution. In late 40s. At the time, we actually don't have a computer. So I want you to remember the algorithm goes before computer. The software goes before hardware. Okay. Because even use your pen and paper, you still have to have a rigorous procedure to find what's the optimal solutions. So the 2 gentlemen got George Dantzig on stage because they said without George Dantzig's method or algorithms, the linear programming model is just an empty paper. Okay, so I just told you, fortunately, in 1982, I went to Stanford, and subsequently, I worked with George Dantzig as my advisor. So my research is on linear programming. Okay, and many offsprings linear programming, like a Markov decision process. Nowadays, they're called reinforcement learning, actually can all formulate as a linear programming programs. Okay. Now, I'm going to talk about the 4 things, okay, and also each one, I want to get some applications. So first is called online linear programming. Linear programming, It's already 70 years old, okay? Actually, more than 70 years old now. But what's the new things, okay? Then I'm also talk about accelerated so-called nonlinear optimization method, which is how this could help to solve a deep learning or training problems, okay? Then I also talk about the pre-trained mixed integer programming solvers and applications, because people are very, very fascinated with this PT and the pre-trained, okay, GPT stuff. Actually, we already use this a lot in our solvers optimization. Okay. Then I talk about the equitable covering and partition, divide and conquer, and also some of those applications. Okay, so I'm going to be at a very high level. Okay, so if you really want some technical details, you can read the relevant paper, or I will be happy to provide to you. Okay. So, what is the online linear programming? I have a table, lists several data. Okay, you can think about there was a fixed selling period or number of buyers, and there was a fixed inventory of goods. So this is called the inventory of goods. 100 pens, 50 shoes. That's what you know before you sell those goods to the customers. He organized this kind of a sale by auctions. What do you mean auctions? Customers come and require a bunch of goods and make a bid. For example, the first buyer comes by 1 pen, 1 shoe, and 1 hat. He offers $100 for these 3 things. Okay? The second customer come in, buy 1 T-shirt, 1 hat. He offers $30 for these 2 things. Okay? So you can imagine, after you collect all the orders, what you can do? You can formulate a knapsack problems. It's called multi-knapsack problems. So each X, you decide is either equal to 1 or 0. 1 means I give these things to this for $100. If this one equal to 1, that means I give these 2 things for $30. Of course, you can also say 0, reject that auction bid. Correct? Okay? So you can formulate just like the linear programming problems I posted before. This is a pi j, this is A1, this is A2. You remember A1, A2 are vectors. Whatever. So this is your B, which is the initial inventory. So that's the linear programming. You can, or you call it the offline linear programming. You can collect all the order information, then decide. So learn all the data, and then do some decision making. However, so the question, now what's the online linear programming? Online linear programming is to sell or not to sell to each individual customer on the fly. What that means? When X1 comes, you have to decide right away, X1 should equal to 0 or equal to 1. That's before you know all the future information. When X2 comes, given whatever decision you made for the X1, then you have to decide what the X2 should be equal to 0 or 1. Everybody got it? That's what is called online linear programming. And the old one, when you collect all the data and solve for each X1, whether equal to 0, 1, you decide all those X simultaneously. That's called offline linear programming. Okay? So, even you sell those, decide those decision variables from left to right sequentially, you still want to maximize the objective function values. Okay? So the question is there such algorithms which is achieve the objective value is almost close to the offline objective value. So this kind of model, of course, there was several applications individually, but the OLP nowadays is basically developed a couple of students and with now Shipra Agrava. She subsequently also proved a very nice theorem for Thompson sampling. And now she's in the Columbia and tenured. Okay. Another student is called Zizuo Wang, and he's also a Stanford student. 2010, 14, and subsequently there was another student in 2022 proved some nice theorems. Okay. Built these whole theories. What's the theories? So this is OLP again, and but this is the offline LP, right? Okay, if you decide. But we have. So what variable, again, let me just put these whole things into perspective. So each variable arrives sequentially together with the data, like PyJ, AJ. Then you have to decide X on the fly before knowing the future data points. So this has to be what? So when you collect all the data in terms of the linear programming, it's like you're learning all the data. Okay? But when you make a decision on the fly, what do you have to do? You cannot learn all the data before you're making decisions. So you have to do learning while doing. So that's what typically from the learning first and deciding second. So most of our optimization, offline optimization is, we'll collect all the data first. Then I decide what's the best solution. That turned out to be a luxury. You cannot do that in the real world anymore. Okay? People has no patience to wait until you decide they can go to the next store. Okay? So in that case, and as you can see, so this provides certain challenge. So one factor you can see, offline LP's volatility value is the upper bound for the online version, right? Okay, because that's the value of information fundamentally. Once you decide knowing completely perfect information, you should always do better than you only know partial decisions. The questions, okay. So the questions, is the optimal online decision algorithm mechanism, something which is can achieve the best you can do. So that's what this LT theory is proved. The paper proved there exists a mechanism or algorithm or decision rules to make an online decision perfectly or the best you can do. Basically, you can prove some negative result. You cannot achieve how much. And then you can also design algorithms, achieve the bound, achieve the best you can do. So that's what there was a sentence below that. So actually, basically, that's the theories. Okay, so this is called online linear programming. Subsequently, originally AGA has to be either positive or all positive. When AGA are all positive means what? The customer coming only buy things. For example, you remember 0, 1 or something, whatever. But what's the second paper, this 2002 paper actually extended to AIGA. Some entry can be either positive or negative. And PyJ can be also negative. If AJ is negative, PyJ is negative, what's that implication? The implication is that the customer become a seller. They sell some resources to you. You have to pay PyJ as your cost. You understand? So that become a buy and a sell market. Okay. Originally, AJ is only provable only for non-active. That's only buyer's market. Now this become a double market, whatever. Buy and sell. Okay. Anyway. So the whole theorems, I'm just give a very, very simple idea, okay? I cannot go through the details. So the whole idea is try to learn and compute the optimal, itemized optimal prices. Suppose we have some kind of optimal price, a quote unquote. Suppose pen, each $45, pair of shoe was $45, and so on and so forth. My online decision would be easy based on those prices. For example, the first order comes, even I don't know future information, because he is trying to buy three, one pen, one pair of shoes, one hat. What's the total also of those three things? 105, correct? But he only want to pay $100. What's the decision for X1? X1 equal to 0. You want to use $100 to buy $305 things. So this is an underbid. I have these optimal prices as my guidance to decide to sell or not to sell. Second one, buy two things, only worth $25. But he is willing to pay $30. What's the X2 value if you want to maximize the revenue or profit? The X2 should be equal to 1. Okay? So that's the whole thing. Okay? And probably this is also called a price mechanism. Is such a price exist? So such that based on those price, when you make the decision sequentially, you can do what's the best you can do. It turn out yes. Okay? And this is come from the shadow price and the theory of linear programming. Of course, you have to gradually learn those numbers. You may be at the beginning make a wrong guess, but after you get more information, you continually relearn those prices, update the price. At the end, you will do okay. You'll do the best you can do. Is that clear? Okay. So for student over here, if you do machine learning, first thing I want you maybe think about it. What's the target? What's the things you want to learn? Okay, and if you don't have a specific target, you cannot just like blend, 瞎子摸象啊 whatever. You have to find what's the target. Okay, what do you want to find? Okay, so that's my advice. So we basically use these prices. And we accept it's over there, and then we basically prove that was optimal online can achieve the best you could do, okay, based on those learning those prices. Of course, there was a prime and the for all these things. What's the application? The very big expression is the advertisement, especially on display advertisement. Okay. So one of students went to advertiser.com and implemented those algorithms. Because each click and you have to, each impression, you want to put several things on the screen to sell them. And each advertiser, the goods provider, they have a certain budget. Okay, when you provide that, the budget will consume. Anyway, so initially they just use some greedy algorithms. And later on, they use this online LP. Actually, Google has heavily used this technology, and last year they won some big prize by using OLP technology. Okay. So this just to show you, okay, if you use this online LP, you can achieve much better revenue. So the optimize like 2,000, you get almost close to 2,000. Of course, you cannot always achieve that, have some stochastic. Other method can do it. A good point by industry people, they think this is like a budget, okay? When you're already over here, that means the budget from one customer is already used up. But here, you make sure everybody's budget is only exhausted at the very end. What's that mean? That means if you use greedy algorithms, those most popular goods, you will show them first. In the first 10 days or first month, the budget is already used up. And the second half, they don't have any budget to show things. But the customer does not like that. They want you show, like Tesla, you want to show them advice throughout gradually uniform through the whole month, not just only show them in the first half month and the second month. Okay, so very, very good. Okay, the online LP paper was was published in 2014. So this is another advice for students when you submit the paper, especially to informs like management science informs. You have to be very patient, okay? And so our initial paper, the result was established in 2010. First, we subject to management science, was rejected, okay, right away. Then we submitted to OR, was, after a couple of major revision, only accepted at 2014, 4 years later, okay? So you have to take it. Don't get too disappointed, okay, when you receive some rejection. Right now, as we talk to Yuan, many papers are almost like a rundown decision right now. So if you really truly believe your research result, just continue to submit, okay, put it in the archive. And if it's the good things, and it will come out. 真金不怕火炼, okay. So be patient. I just want to, the paper cited multiple hundred times now. The one company cited the paper most is from Alibaba. Okay, almost 10% presentations for that paper, OL papers, come from Alibaba and the researchers. Because why? Because they need a lot for online decision making. Okay, so first they call the fulfillment. Okay, some of the Chinese. So basically say, once you make orders, multiple items, well, those items should be fulfilled by which warehouse or which manufacturer or which places. Okay, so that's as the online decisions. Okay, so there's another paper cited this paper because they said once they give the bonus red back. I don't know, maybe Kuaishou also do those kind of things, give them some those things, okay? Anyway, so I just wanted to mention, it has been another application now is online algorithm banded with knapsack. So just was mentioned some things can work for MDP and the multi-knapsack with knapsack. What is the MDP? What's multi-banded with knapsack? Now, in the traditional banded problems, you only have machines. You want to select the machine with the highest return rate, correct? That's the multi-arm banded problems. But however, in banded with knapsack problem, knapsack are replaced because they have a resource constraints. So when you pull a banded, you need to consume some resources. It's like you do one trial, one test, you need resources, okay? So how many tries you can find the best arms? With banded constraint, suppose you have M resource constraint. Your problem is not to select the best single arm. You want to select the best M arms together. Because each time use different resources. So it's not like you select the best, then you select the second best, then you select the third best. No, that top M may not be the best, give you total values, right? Okay? You know why? Because the best one and the second best one may not get along well, okay? And, because they hate each other, and they very, in Chinese, like very 卷, okay? Don't get along. So you have to select what's the best M arms. It's not only sequentially select best, and then second best, and then third best, okay? Because they correlated. They very, okay, so very, very interesting problems. So in this problem, another difference from online algorithms, you are not waiting for customer come here, make an offer. You, decision maker, you are the market maker, you have to go out, search to which customer to give them to sell. Okay? So there's more active sales, this kind of things. You're not wait for them coming. You actually go out looking for the best one, with the M7 one. Okay. So anyway, so this best way, because of time, I just wanted to show you, and we established the best so-called log T regret, which is sublinear. This log T regret, which is the lower of this value, the better of the algorithms. Okay, T is like a number of customer or time horizons. Okay, number of tests. So log T is the best you can do. Okay, so the paper was in 21. ICML was, I believe, a student give a long presentation. I think ICML has something like a long presentation or short presentation or some poster, all that kind of thing. Okay. So there's many applications. A third application is another interesting thing. Okay. So in the previous examples, I compute and then those best prices. But I'm not post those prices to customers. I keep those prices as my decision reference. It's like only use them internally. It's the private information. But however, in the real world, if you want to emphasize the fairness or envy-free, you should post those prices. Not the user decide to buy or not to buy, or buy what. Everybody understand all the questions? Okay. So this is so. Do we have a price post or post price mechanism? Still can do much better. Okay. So many people probably heard about in the market. Okay. Of course, this is long time economic phenomenon, right? Whether given you have a goods quantity available, given many customers, they have the budget, they have the utility functions, they come to want to buy the goods. Then economic ask a question: is there so price put for each of these? One customer buy according to those prices optimally, envy-free. Then all the goods are sold out. No more, no less. It's called the market clearing equilibrium. So this has been fundamental, okay, for Western economic or decentralized or market economy. It turned out, yes, it exists for any given budget or consumption. But that theorem is developed in a static way. When you connect all the information of the customers, the utility function, the budget, of course you know what's the available supplies. You can compute those equilibrium price because they exist and can be computed. But what about in the real world? First, each budget or each data points maybe it's not completely determinant. They maybe have some idea, okay? Each time they appeared in the market, depending on whether it's the morning or whether it's the night, maybe they feel difference. They may have a single mean value, okay? But they maybe behave differently. Is that static equilibrium still can clear the market? Okay? So we ask this fundamental question. So this is a work we just did with Gelota, and it's the ICME student the same. We ask, what about the stochastic market? Which means each agent showed up in the market with certain uncertainties. You may evaluate the mean, but they actually always have a little bit of variance. Can that equilibrium, can that not say, oh, no, you just compute the mean, use that mean, compute the market equilibrium price. Is that works? It turns out it's not working. You will induce very large errors. Okay? So the question is, whether you have a sequence of updating prices. So here's the mechanism. So what the first agent T is come. When agent T plus 1 comes, I have to decide what's the price. The price could be different. You can think about this, the new price. Then the agent, based on those prices, decide to buy which item and buy how much. I don't need to know the information. I don't need to know the, the utilities value. Or basically observe what they buy and buy how much. I can use that information based up, and also based on all the previous POC information, I can have a mechanism update the price. Okay? And overall, you can prove you can still achieve almost the best you can do, given this uncertainty. So this is the first price posting mechanism. That user, what's the advantage of this? The marketplace and the maker does not know too much detailed information. Okay. We can still sell the market, almost clear the market, with sublinear regret stuff. So this is so the market is called Eisenberg gauge social welfare. Okay. You can prove you'll finally still be able to teach social welfare close to offline, or completely perfect information. So this is the one. So that's about 9. So there's still many open questions. Most of those proof right now is based on IID. Customer, each customer, they have their own IID, the samples. They may be different IID, whatever, but it's still IID, whatever. Or customers is deterministic, but arrive in a rundown order or something like that. So my research right now is focused on non-IID data. Okay, for example, Markovian data, or data like a stock price, or data like a pandemic wave, whatever, those kind of data, whatever. Can you still achieve? Can you still learn from those data, whatever? Okay, so if you're interested, you should take a look, because a lot of real data is not completely independent, like Markovian data. Today's data point depends on yesterday, okay? But it's not completely independent. Okay? Now, my second topic is I'm going to accelerate this one, is what's the deep learning or deep network training? They actually solve a long unconstrained optimization problems. X is like those weight for those neural network, okay, for each edge. This fx is some kind of loss functions. Okay? You want to select x such that this loss function is minimized. This is typical regression. You have a lot of samples, you know what's the outcomes. You want to select those x weight such that the neural network will produce the same result as the correct output. Okay, so those loss functions. To our mathematical optimization researchers, this is just like unconstrained optimization problems. You find x, you minimize fx. Okay, well, for many people familiar with mathematical optimization, once if you have a continuous functions, especially if you have a differential functions, the first one you think about is the so-called gradient vector. Have you heard about a gradient vector? This is just like a partial first-order derivative with respect to each component x. Or if this function is second differentiable, second order, which means have a twice derivative, second order derivative, then you can compute what's the hashing of this matrix. It's just hashing is just a symmetric matrix, okay? Have a double second order derivative. Typically, optimization, one optimization theory says, if you want to find an optimal solution, x sub k is the vector. To be optimized, you have to specify first order and second order necessary conditions, if you take the numerical. First order condition, the gradient vector evaluated at this point should be less than epsilon. If epsilon equal to 0, that means that's perfect, okay? And also the hash matrix at this x here should be almost positive semi-definite. Here I say smallest eigenvalue should be greater than negative square root of epsilon. Here I put epsilon as the small positive number because no algorithm can only get absolutely correct solutions. They always get an approximate solution with accuracy epsilon. Okay? Now the questions. To achieve this objective, for a decision variable in n-dimensional space, how many arithmetical operations are necessary for algorithm to compute that solution satisfy those two conditions? So that's called the complexity theory or theoretical analysis of algorithms. Okay? So this is a very intrinsic, does not matter which machine you do this. Of course, you can maybe also analyze what's the parallel complexity or those kind of things. But the first one, you want how many arithmetical operations. What's the arithmetical operations? Addition, subtractions, multiplications, divisions, and a comparison. 5 basic. Give two numbers, which one is bigger, which one is small. Okay. So those called arithmetical operations because all algorithms in the floating machine are implemented based on those 5 arithmetical operations. Okay. It turned out we have so-called first order method. What's the first order method? Only use first order derivative information. Those algorithms typically need n squared epsilon negative 2 arithmetical operations. So the smaller epsilon, the larger of this number. Have you see that? Okay. But this is the n squared. But the algorithm only generates a solution satisfy first order conditions. So that's another drawback, first order method. Of course, there was also second order method. It's more expensive method because they use the second order derivative informations. Those algorithms typically need n to cube epsilon negative 1.5 arithmetical operations. Compare these two. N3 is much larger than n squared. Especially in today's big models, people talk about the billions, trillions, number of variables. 1n equal to trillions, and then you cube it, it's almost like intractable. But however, the epsilon is negative 1.5. So in terms of the epsilon, this algorithm is faster than this algorithm, correct? However, the n cube is very killing factors. Nobody be able to use n cube operation for any deep learning with today's big models. Okay? So, but this algorithm also achieves additional good things is satisfy second order conditions. Now, is there any improvement? I just wanted to show a couple of results, recently theoretical results. You can still get a homogeneous algorithm or dimension algorithms such that satisfy those two conditions only need n squared, same as the first algorithms. Epsilon is negative 1.75. So this one, it is better than this, correct? In terms of epsilon, this one is worse than this, but still better than this. Besides, the computer conditions satisfy both first order and second order condition. Okay. So I'm not going to go to details. I just wanted to show you this has been tested and solve some kind of like a policy optimization reinforcement learning. Okay. Reinforcement policy with deep learning models, policy optimization is MDP problems, but it's nonlinear. I just want to show you, I don't have too much time, so this is a traditional method, this is a new method, this is a learning rate, okay, on 2 different problems. This is the generalization rate and also on 2 problems. So the blue curve, the higher the curve, the better the algorithms, basically, okay. So I'm not expert, so my student did all those experiments. show this new algorithm. It is better than the older ones in terms of the quality of the solution. Okay, well, but still need epsilon. Can we even could do further speed up? Because the previous algorithms, they instead of solve system linear equations, n-dimensional, they actually solve eigenvalue problems. But solve eigenvalue problems still very costly, extreme eigenvalue. So it's the better way to do is, this is called the dimension reduced method. I'm not going to go to details. So what's the dimension reduced method, a second order method? You create a few directions. Most popular one is the gradient direction and also momentum directions. In that two-dimensional subspace, you apply second order method. So that method turns out to be two-dimensional second order method. Okay? Then you can do a lot of things over there. I just want to give you an example to show why this method, again, the two-dimensional second order method is almost as fast as the first order method because it's only two-dimensional. Okay? You can prove n squared. And I'm going to use this example to show you. I don't know how many people heard about this. It's called the sensor network localization. Professor Yao also active doing research among this one. So basically say, you can think about each of these dots is like a sensor points. Okay? There was a big dots, you can call this the anchor points. So we know what's the coordinate position for those anchors. But for all those small dots, I don't know where they are. Okay? It's the blank to me. However, if every two sensor points, if those dots get very close, I can measure the distance. The question is, from those three anchors, from all those small distance information, can I find what's the location for each of these small dots? Everybody understand the problem? Okay? So if you know the position, XY position on the plane, then compute the distance is easy, right? I'm talking about a Euclidean distance. You just take the difference, take two norms. But here is, you know some two norms, but you have to go back, compute what's the location. It's like inverse problems. Okay? This has been very, very popular in the logistical operations, warehousing. People talk about the Internet of Things because like an Internet of cars, and because cars are moving around, I cannot chase them. You may say, oh, I can use the GPS or something, but however, we talk about the Chinese-American relation. If there was a war, I think the first things to go is the GPS. Well, we'll go, whatever. Okay, all the satellites will be shut down, right? What kind of things? Okay, so people interested in develop GPS-less localization technology. Okay. Besides, who localized those satellites? How will GPS work? We use the satellites as anchors. Okay? We find our distance to a bunch of satellites because we know satellites like anchors. But now people talk about satellites, it's just actually they're randomly moving in the sky right now. Okay? It may not follow a certain orbit because orbit is already occupied. Okay? So even satellites is like like a lost, okay, and 流浪啊，都在流浪 running around. Okay, so how to localize? So actually, I have a student graduate, is the student me and John Ducci, and he actually went to Apple. Apple now organized a special group do satellite localization using SDP, whatever. Actually, it's tractable. Anyway. What's the mathematical problems? You said that's easy. I just found the xi, the two coordinates, and talk about on the plane, simplification. Xi minus xj, j's, the unknown variables, the location, xy location for j's. I just need the two norm equal to dij, which is the distance I know, right? So if you say norm, take a square root is not good, I just square them. So this is the xi become acre. Keep in your mind, dij, Only when you get very close, you know the distance. If you're too far away, you don't know, okay? So this is called the unit disk graph. So the questions, from those distance information, some anchor information, can I solve these system equations, finding xi, xj for all the xi and j? It turned out this is the very, very hard problems, okay? Unlike linear equations, you have a certificate, whether solvable or not solvable, whether solution is unique or not unique, or whether solution exists or not exists. But for system of quadratic equation, so far we don't have a good way to track them or certify them. Well, many people say, oh, instead of solve system equation, let's solve these nonlinear least squares. Okay, what's the nonlinear square? That's my xi, xj, unconstrained or minimization. That's the loss functions. Xi, xj are one of these square equal to dij square. Then I take a square again. If I have a solution satisfying equation, this objective value would be equal to 0, correct? That's the global value, because each term would be equal to 0. But as you can see, this is squared and squared. If you don't square over it, you still become a non-convex optimization problem. Okay? So this would be a good test problem to test our second-order method against the first-order method. So here I'm just giving you examples. We start from same point. We have a little bit noise to the distance, because in the reality, distance always have some noise. So this is the solution generated from first order or gradient descent method. We also tried ADAM. We also tried a stochastic gradient method. Typically behave like this. Cross is the true position of that point. Red is what solution generated by the algorithm. You see, many cross is not circled by this red one. Which means the solution generated by the algorithm is far from the true locations. Because for this term, I know what's the true locations. Okay. However, use the second order method, start from same points, they generate much high quality solution. Because why? Because I use the second order information. Because it's not going to provably give you higher quality solutions. Okay, the time is a little bit longer, not significant, 1.3 times more, but you get a much higher quality. So you can do now, for example, this is just the 10,000 points. No, that's about the number of satellites is going to be in the sky. You want localization. So again, there was a big difference, and I want to save for time. So yeah, so this is just the amplifier of this. This is the generated by second order method. This is generated by the first order method. Okay, so I don't have time. Because our solution is so fast now, we can every few seconds we can track those satellites' movement. So it become a like a sensor tracking problems. Each time I resolve it, and do those things. Okay. Very recently, we also developed the theories. For these functions, I ask a student, suppose I say I allow the distance to be more and distance information increase. Okay? Which means what? Which means I improve that radial range. It's like every 4 points, I can measure the distance in a longer radial range, whatever. So this should be good for minimize these functions, right? So I ask a question. Is the value, is those knowledge, those information are more than enough? Is this problem become a convex optimization problem? Or so optimals or every local minimum of this would be a global minimum. I want to understand what I'm trying to do. This is also asked for me. I have loss functions based on samples. If a sample increases, the function behavior should get better and better, because I have an infinite sample, and then my solution quality out of this regression model should be better, right? It turned out, even I know every distance between 2 points, local minimum always exists regardless of how much edge information you have. Edge, which is the 2 points connections. Okay? So this loss function does not improve. In terms of optimality, still face a lot of local minimums. Then we ask a question. How about we do dimension expansion? What's the dimension expansion? Instead, keep of those n variable x, I create the higher order variables. For any xi times xi, this is the inner product I call yii. For xi times yxj, I call yij. So I call yij. I introduce those y variables represent the correlation between the two variables, 2x. So how many these y variables now? You have an n squared, almost n squared. Of course, because symmetrically, but still in the order of n squared. So I do dimension expansion instead of dimension reduction. Okay. Then, of course, we know these relations. It turns out by adding those y variables, I can force this kind of constraints. And if I require this matrix, this one, if I is two-dimensional, this is n plus 2 by n plus 2 dimension, again in the n squared dimensional. Okay. If I still insist these problems has rank D or rank 2 in the 2 plane, this is the same formulation, still non-convex optimization. Even you augment the dimension. But it's very interesting how with rank constraint, the theorems, this convex realization, if I ignore these rank constraints, this problem become a convex operation in high-dimensional space, has a unique solution when edge information is sufficient. What's the takeaway? The loss function, the regression function you constructed, if you does not do dimension increasing, does not do dimension expansion, they're always like non-convex optimization problems. However, if you do a little bit of dimension expansion, these problems, when information is enough, become a convex optimization problem. Just rely on information increase, amount of information increasing does not do job. You have to also increase the dimension of the problems. You probably heard about this. This is why today everybody go for big models. Okay? And also this transformer actually introduced a lot of additional variables as the product of those parameters. But this phenomenon is already known in terms of the sensor network localization. So we have some theory proved by Anthony and also in the CUHK. So I would say this is called the blast of dimensionality. You probably heard of the word, it's called the curse of dimensionality, right? Think dimension increase does not work. But sometimes slight dimension increase from n to n squared actually makes the problem behave much better. Okay? So that's something in your research you can think about it. So I'm already done. Okay, I just wanted to, the third topic I wanted to do is very popular. It's like integer programming problems, which I posted at the very beginning of this talk. It's the knapsack problem. Some variable has either 0 or 1. I still remember what? You have a linear program, you also have a variable. So this happens to so-called unit commitment of power grid optimization. I think a couple of students organized this cardinal operations called Shanshu Keju in China. They're actually working with the Nanfang Dianwang, okay, Southern Chinese Great Wall Network. What is the problem? The problem is decide. It's called day ahead market. What's the day ahead market? Before each day, you have to plan which generator to turn on at which time. Okay? Which hydrogen or radiology, which whatever, give all these kind of things information. So you have to prepare for the next day, how much electricity should be generated, if they were generated that much, which huge generator. And also you have to do network transfer. So each, for example, the whole network compute the 10,000 generators plus also have hydro. You have hydros, okay, I didn't put hydros. Now you also have all the wind generator and the solar generator and all these very complicated things. So you have to carefully plan. Why? Because the electricity is the tricky things. The supply should be always equal to demand, okay? At any time point, you cannot, okay? So it's the millions of constraint variables. You can do all these kind of very large regions. This can be formulated as the linear programming with binary decision variables, 0 or 1, okay? Another problem is scheduling problems. So Shanshu Keji now working with Beijing Gongjiao, okay? This is the largest public transport companies. What's the problems? Because company all use plug-in electrical cars now, okay? So those cars have to recharge. How to scale, for example, one Beijing you have, 20,000 cars, and which car charge at which time. There was a scheduling problems, okay? Yeah, you have to smart charge them because you have to maintain before the battery running out. You have to charge them, whatever. So everything has to be very carefully planned, okay? And also decide which time to charge. Also affect the power grid peak time, peak demand. For example, if you choose naive charge, the black one is like a daily electricity usage. Peak time is about afternoon time. You probably already know this. However, if all the cars, this is a picture with suppose 25% of California cars become electrical. If they charge randomly according to the linear, the peak time will increase. But however, if you optimize the charging schedules, they actually can reduce peak demand. Because why? Because all those battery become an electricity storage unit. You can discharge to the power network, okay? Anyway, so this can be formulated as an integer programming problem. So I'm not going to go there, okay? So this is already the select, try to make this for 14th, 14路车, Beijing. I don't know which people come from Beijing, probably it's a very long route, very popular route. Everybody also know how the high-speed train was scheduled and also since. This is the Beijing to Shanghai, one of the most popular high-speed railway schedule. It's two problems. One is called the TTP, time tableau. So this is from when you started the day, end of the day. Each of these curves represent a schedule of a high-speed train. Okay, so this is from Hongqiao to Beijing South. From here is Beijing South to Hongqiao. You will never let these cars to be crossed at the same platform, because you will collide. And each one Between each random, you only have one route to use that high-speed array. This has to be very, very carefully scheduled. So as you can imagine, schedule those things, which time, which train, at which platform. So this is called TTP, the train time tabling problem. Train platform problem is called the TPP. This has to be all very careful. Traditionally, what do they do? They use very, very experimental engineers, okay, and organize. Usually, if you want to have a new timetable, in China we call the 列车时刻表, whatever. You usually need 1 month to do this. So that's why you cannot adjust too often, because too time consuming. Safety is the most important thing. What do they do now? Now we can use binary integer linear program solver. Make such one, for example, we can actually insert 584 trains a single day. We can use 1,000 seconds, okay, to finish this, meet all the safety requirements. So what that means? That means we potentially can make a new time schedule once every few days to dealing with those uncertain demand. So if we know pandemic coming, we know not many people travel, in 1 day we can come out a new time schedule to save a lot of energy, a lot of costs. Okay? So what's the speed up? This is a research questions. As I said, mixed integer programs, very, very hard problems, okay? However, in our optimization developers, we already have some old technology. It's called the pre-trained heuristic. What's the pre-trained heuristic? We basically treat each variable y as a binary variable. Suppose binary variable, each y should be either 0 or 1. What we can do? If we solve this same type of problems for one instance of a specific problem instance many, many times, we should get some knowledge, right? Which variable likely to be equal to 1, which variable likely to be equal to 0. If the information are perfectly matched, of course, because the information is never exactly matched, so we still have to resolve it. But however, those knowledge can still be used for us to retrain, to accelerate these new solvers. Even my input data are slightly different from the older one. Already understand questions? Okay. So what we can do is we can trade we can collect all the older data. Some variables is equal to, in these scenarios. So first scenario, mth scenario, we know what's the y. Then we can compute what? We compute how many times this is equal to 1s. We can divide by m, we get what's the fraction that variable equal to 1, correct? Okay. Then we use this as what? As some kind of knowledge training. So people use this, for example, you can use all of things to retraining those models, okay? Use this information, for example, maybe this variable, we can fix that variable equal to 1 even before we numerically solve the problems, okay? So the good news that, yeah, it's sometimes quite mature, quite effective, but the question is, you still have a risk. Even this variable in all those scenarios, 99% actually indicate this variable should equal to 1. If we fix them equal to 1, for the new data, the optimal may still ask that variable equal to 0, whatever. Okay? So this is it's just like typically ChatGPT. They can give you most of the time 99% give you very good answers, but they can fool you one time, whatever kind of things. Okay, so this is something which is the sense all the learning does not give you 100% guarantee the solution is correct. Okay, and also we have training have to depend on all different problem. So each different problem instance may have a different patterns. So this is not like ChatGPT. You can train in because everybody have a common values. So when we train in ChatGPT, we have a common objective. Okay, it's more like a model tongue. Of course, well, maybe China, US are different value, what kind of sense. You may train differently, but more or less, people, which you think is good, most people probably think is good, whatever. So we have to train. So that's the risk. Training of data, again, has some risk. I'm not going to process statistical, simple, efficient, provable. What's the idea? We treat those. So this variable in the past 100 times, it equal to 1. So only one time equal to 0. So we think this is the 0.99. So 0.12. So which is the same variable. Same problems, okay? Just different input data. We can interpret each value as likelihood variable take 1, right? In the optimal solutions. If you think each of those data points are independent or IID or something. But each variable introduces some risk variance, right? If you decide each individual to be each one, it's like binomial variables, okay? So that dealing them separately result in extremely risky outcome. You may have one variable, you make a wrong guess, either 0 or 1 for the new data, you screwed everything. What should we do? What should we do? Reducing a bunch of risk guesses to reduce this wrong patch. What do you do? Put them in a pool. Aggregate them. What do we do? Very simple technology. For those variables in the previous one above 0.9, I add them up, greater equal to 0.9 times the total number of variables. For those equal to 0, 1, and 1, I'm not guessing each individual to be equal to 0. I ask among all those variables, not many of them equal to 1. Most of them equal to 0. That's the intuition. We pull each of the various variables together, make those cardinality cut. So if we add these two cuts into the optimization problems, so those get the cutting planes, okay? So intuitively, we know these two inequality are expectedly hold for alpha equal to 0.9 because everybody is above 0.9. So this one, everybody is 0.1. These two inequality are exactly cutting planes for integer programming solver, okay? So the issue is how to use alpha beta. Well, you can use a binomial concentration, what kind of things, depending on how many what's the aggregate, the total variance, and you put 2 sigmas, 3 sigmas, or those kind of things to choose what's the alpha, what's the beta. And also, we add those two cutting planes, this also have other possibilities. So the question is, so you basically create this concentration inequality. So basically, we basically add these two cuts. So the intersection of cut this part, we think the optimal solution mostly likely in these regions. Of course, you can still have two other things which are less likely. For integer programming, for best solution in this region is extremely unlikely, whatever. Okay, you can use this concentration. Then you can do computing. You first emphasize this, compute the solution, which already give you a good integer optimal solution. So that'll give you a bound to eliminate many solution branch. That if you know integer program, basically branch and branch bunch. Okay, most likelihood region I just wanted to show you what's the speed up for the state of art mixed integer programming solvers. So Groby, probably for people in our OR department in GHUST, they all know what's Groby. This COPT, this is Chinese, 参数科技 or whatever, mixed integer programming solver. By use that technology, this table indicate is all this. There was 20 problems over here. So solution time speed up is how much? For example, for this problem, global speed up about 2.5 times. I mean, 2.5 times. Okay? It was maybe like, you need 10 seconds. Now only need maybe 4 seconds or whatever. Okay? This is the speed up for global. 20 times. This is to solve those, I think this is for solve like knapsack problems. Okay? So the speed up is uniformly using that heuristic cut. So I call those cut a statistical cut, whatever, a likelihood cut. It's not, but since we still keep all the options open, you won't miss the optimal solution. So it's explainable. Okay? So this is speed up or knapsack instances. This is a speed up for, so this is for unit commitment. And also the same problem for electricity grid. This is for set covering problems. You can see, even for global, by using this newly, you can think about this as the machine learning. How machine learning help to solve optimization problems, because those cuts are pretty much like a statistical and from machine learning problems. This improved 36 times faster. So that means if you need 1 day to solve the problems, now it's what? You only last 1 hour you can solve the problems, because the speed up is 36. And also very, very uniform. So what's the message? This kind of pre-training, which is very popular for GPT, you can use the same philosophy to training your optimization solvers, which is mainly used for scientific computing. And also, the technology is simple, explainable, and also provable. That's unlike GPT, whatever. We can guarantee optimality, whatever. Okay. So finally, 5 minutes, okay. Maybe I just want to give you many students, I just wanted to show how people, I know some education very famous for mathematicians, and I just give you a very, very simple problem, geometric problems. I give a convex polygon, okay? I give endpoints already pre-distributed in this convex polygon. Endpoints. Now, I want to partition those big polygons into n pieces, n subregions, satisfy the following. Each subregion is also a convex polygon. Each subregion contains one of those given points. This big polygon have endpoints. I want to chunk them into n pieces. Each piece is still convex polygon. What is the convex polygon? That means give any 2 points, the 9 segment is still in the set, right? So every point have I can in my C side, whatever. What's the third condition? All subregions have an equal area. Okay? 平面结合问题 okay? Is that possible? The location of those endpoints is arbitrary, okay? Of course, they are in general position or something, whatever. And they're not, concentrated on this, not degenerate, basically. Every 2 points are different.
Just one quick question.
Yeah.
Visibility guaranteed for any kind of random?
Yes.
Always guaranteed.
It turns out already guarantee exists. Okay? Always guaranteed exist. as long as this is a convex polygon, endpoints are arbitrarily located over there. You can always partition those, chop those big polygons into m small polygons. Each one is convex, contain one of those endpoints. Each region have an equal area. Okay? Why equal area? You can think about this point is like a server. The customer uniform distributed over there. Once you have this small convex polygon, that means all the customer in that convex gun should be served by the points inside that polygon. How do you understand? The equal area means each point serves same number of customers, which called the equal demand. Okay? So, you probably heard about Voronoi diagram. This is Yao Yuan's topology stuff. What's the Voronoi diagram? For every 2 points, you draw a middle perpendicular line, right? 中垂线, is that right? Okay. Then you chop those polygons into NPCs. Each one is also convex polygon, and each one contains one of the point. Correct? Is that right? Everybody know how the Voronoi diagram was drawn? You draw a perpendicular line. But what happened? It's not an equal area. Some regions are very big, so this server will be very busy. This server would be very light. That's not good. Okay. So this is the John Carlson, okay, and it's the Carlson's son, whatever. It's the son of the professor in the Stanford, he's famous for topologies, right? And he actually have a PhD thesis on this. Basically say, not only such a partition exists, you can do it very fast. And also, firstly, it's not enough. Also, motivation is try to do how to do divide and conquer, and these servers. For example, this has been tested in one of the telecommunication giants in China. So what happened? When I say equal area, it does not need to be equal area. The customer distribution may not be uniform. It's just the number of customers served by one server should be about the same, whatever. So it's that integral should be the same, whatever. Okay. So this actually is proved by very famous ham sandwich theorems, whatever, in mathematics. Whatever. You can always do this. Okay. So here's the question: each server is like towers, wireless tower. Whenever you have a cell phone will automatically connect to which tower, right? You will be served by that tower. But sometimes one tower gets too many communications, some tower maybe get less. So people want to equalize the business of those wireless towers. So in this case, we have to repartition. So when they repartition those regions. So anyway, they do the field test. If you don't adjust, okay, for example, because the daytime or the nighttime, the demand distribution may be different, right? You have to repartition this tower server average, a region. So if you do this, the busy become night. Yellow means very busy. This one, again, is very busy and become a little bit better, whatever, lighter. When you have more greens, that means the better, whatever. So you can do this rate, divide, and conquer. Because the algorithms are fast, you can do this response. It's more like a data-driven, whatever, whenever you change. This is the final 1 minute. I just wanted to show you another application. This is application number 10. It's called the Street View applications. I don't know how many of you, this is also John Carlson did about 15 years ago with some map company. How map company update street information? I don't know, 高德地图, Google Map in the Europe, whatever. once every while, they will send a vehicle mounted with 3D cameras to go through every street of that city to collect 3D information, then compare to all the information to see which things changed, which data should be updated. Is the new building, or is the two-way become a one-way, or one-way become two ways, whatever. So you can imagine, if I want to send one vehicle traverse street, the whole city, it's very, very hard. Take probably months to finish. So what they do is they send 100 vehicles to do these things. Hopefully they can finish, everybody finish in one day. Okay, they hire some taxi to do this. For example, that become, okay, hire some even buses. If we have a bus route to traverse all the street, then we can use those kind of things. But anyway, most of the time they hire a taxi. Okay, so the question is, how should I divide this map into 100 pieces? Then 100 regions. Now every street in that region should be scanned by that single vehicles. I have to guarantee everybody finish about the same time. Everybody understand? Okay. So this is something I want to show you. This thing. So first, the two stages. One stage is called partition. So this is from John Carlson. Okay. So this is the initial location of those vehicles, which have to be. You see, the partition is done. Now, what do they do? For each vehicle, what do? They plan in the route. I don't know how to plan the route. Which street go first, which street second, which third, which that. So you have to, you hope to scan your whole street in a minimum amount of overlap. Whatever. Hopefully, every street only need to go once. That's the best you can do, right? Because you have to traverse all the street. Of course, you can also think about. And also during the route planning, the company also asks us, you should make most right turns instead of left turns. And that's the realistic one, because the left turn take a longer time, waiting time. That's not Hong Kong. Oh, that's right. So yeah. So anyway. So yeah. So what they did? This company is in Germany. Hopefully, it's right turn. So I just finally just a small video. The company actually put an advertisement to show the technology.
This is a revolution in map making. This is how hyper-accurate, hyper-detailed map collection gives rise to more powerful, innovative location experiences. This is Navtec True.
That's the European map company.
Navtec True helps us create the most true-to-life map.
That's the camera.
A 3D model of the real world. Navtec True is a unique combination of technologies that enables us to mirror the real world with unsurpassed fidelity. Equipped cars drive roads while the Navtec True system captures a 360-degree picture of the world. The rotating LiDAR collects over 1.3 million 3D digital data points every second, collecting details as small as letters on signs or lines of a crosswalk. True's highly accurate positioning sensors, such as GPS, IMU and wheel encoders, ensure that the data is collected with incredible precision for every data point and every attribute within that data point. Sophisticated pre-planning and monitoring tools make the most of every road trip. Advanced and highly efficient routing tools enable an ideal ratio of distance driven and information collected. Automated processing capabilities allow us to transform the huge libraries of raw data into location content that is the industry's most comprehensive and accurate. our ability to automatically recognize features in reality improves our efficiency and quality of maintenance. Globally distributed teams analyze and validate the results from the automation process and make sure they are quickly incorporated into our map. Key navigation attributes like speed limits, warning signs, traffic signals, and lane markings help users make decisions easier, even when confronted with complex situations. High-quality footage from True is used to identify changes for advanced driver assistance systems. The accurate 3D views based on accurate infrastructure mapping. Navtech True brings scale and efficiency, taking our data quality to the next level. This is technology that is creating the world's most true-to-life map. This is Navtech True.
Now this is the, you can think of this, used a lot of different technologies. So it's a smart routing plan, just one small part of it. That's what I'm talking about. Divide and conquer. Whatever. Okay. So I just want to overall, it is possible to make online decision or quantitative decision deals with performance guarantee close to that of the offline decision making. So how can the online decision, offline decision, online decision? Because in today's society, everything becomes very busy. You cannot wait. Okay. So second order method, even in low dimensional space, still better than pure first order method, especially for people do deep learning. I strongly advocate if you maybe will make your life easy. Whatever. Because today's training a big model use first order method, take $1 billion, whatever, take a longer time. Maybe small algorithm will be reduce the cost because make it faster, whatever. Okay. But I'm not in that area, so I don't know much. Okay. Pre-training greatly improve mixed integer LP solver that benefit the real economy. The three integer program example I mentioned is the real problems. Okay. So people have to deal with. Decomposition, divide and conquer helps solving very large scale decision and computation problems. So many people ask me, oh, we have a ChatGPT. Many people don't need to do the research anymore. But I strongly disagree. Okay, so this is a scientific computing. It's not like ad hoc, you know. Well, human feel this is better, or this sentence is better than that sentence. No, it's not. We have very rigorous magic. Which one is better, which one is not, okay? So I don't think you can launch a satellite to the moon or something by using ChatGPT as your guide, as your pilot, whatever. You still need to be more rigorous, more scientific. And each problem is different. It's unlike something, you know, write something, articles, okay? And you always turn out to be the similar things. Well, that's not good. Okay, so as our profession should be safe. I'm very proud. Okay, and thank you. Yeah.
Thanks a lot for Professor Ye's lecture. It's so many mathematics. So we are happy here. We won't be get lost losing jobs because of ChatGPT. That's your future work. Any questions? Feel free. I know many students from my PG class also here. So I give you some homework to ask questions. Hopefully you can do this. Any questions? Maybe let me one question first. For the divide and conquer, did John Carson starting from the Voronoi cell and try to resize it toward the equal area?
No, they have two approaches. One is to start from scratch, to use different technology. It's like they basically say they can prove the theorems. For example, if you have a even number points.
Okay.
Then your first thing you draw is to draw a single line. Divide that region into two pieces. Same area, same half number points.
I see.
you can continue to do this bisections, whatever kind of things. If you have an odd number, you can use 2 lines to draw those things, whatever.
Oh,
So you could, it's like a tree and continue to do those kind of divide. Yeah.
I see. It's
Yeah.
not a Voronoi
It's
diagram.
not, then later on, people think maybe Voronoi diagram have a better shape. They use some adjustment. That's right. Move those 中垂线 a little bit further right or not. It's not like a 中垂线 and the middle perpendicular line is the off the middle. Whatever.
I see.
You can here use the both method. Whatever.
I see.
Yeah, that's a good question. Yeah.
Okay, thank you.
Yeah.
Other questions? Yes.
Yeah.
Thank you, Professor. Yeah, okay.
Yeah.
Very interesting talk. Okay,
Oh,
give a
thank
lot
you.
of problems,
Yeah.
and I could not follow the last 3 problems. The first one, okay, maybe I get a mathematical question about
Yeah.
the very first online linear program problems, and you get a customers, and they have a. I assume that they have a utility function. They can buy the goods they want.
Yes.
Okay.
Yes.
And then you collect this information. And this information, they make a decision and you give it the price.
Yes.
Suppose we give a price at the beginning, no matter what it is, initial price.
Yeah.
Then the customer responds it and buy their one. You collect this information.
Yes.
And the sellers, okay, use this information and give it the second time the price.
Yeah.
And then this one we get the dynamics of about the market.
That's right.
And my question is that, okay, that when this continues, okay, like a sequence of prices, okay.
Yes.
So the question is that, is this a prime, okay, the prime will converge into a limit one, okay, whether it exists. If it doesn't exist, whether it's a periodic cycles over there. Okay.
Oh, yeah.
That's what I'm asking for about it. Yeah.
That's an excellent question. Yes. Right now, we prove this convergence to a ground truth. Assume each customer still like an IID, whatever. Okay. So then, if this is an IID, you can prove convergence. You can prove nice and things. If the customer become like a periodic or something, whatever, I think we need, then that means that the customer is not completely independent anymore. Something all comes in, or all don't come, or all come. And it's like a cycling. Then we need
Depends on the distribution.
Yes, right.
The priority distribution
Exactly.
of the market.
That's the market. That's right. So right now, dealing with those non-IID, non-stationary distribution, we still have a lot of open questions. Yeah. That's correct. That's the key right now.
Okay. Is it possible that if we assume that customers, okay, that you get many customers over there,
Yeah.
and they may have a preference,
Yes.
and if they achieve their maximum for all the customers, and supplier as another customer, probably inside one, okay, what is like the economic general equilibrium. You can achieve the equilibrium where the price exists over there.
Yeah.
Like a general equilibrium, like Arrow de Broglie model, something.
Yes, right. It is like Arrow de Broglie, whatever. Yeah. So the beautiful theorems is about this feature market. They have a social representation, whatever. It's very decentralized. But still can come out with the aggregated like a social optimization model to prove exist of equilibrium. That's right. The price of this way updated actually under certain assumption you can prove converge to that equilibrium.
That's good. That's interesting. Very interesting.
Yeah, it's the one way to dealing with those kind of, because we don't know information. Then what's the usage of those equilibrium price? Unless we can nail it and gradually but still do the job, still let a customer be happy.
It's kind of such a research is done already. Okay. I mean,
It turned out dealing with
known,
dynamic equilibrium, this especially uncertainty, each customer is not, because all the exist economic theory is based on perfect information, and each agent utility value function is fixed. Right? But even for each individual, sometimes there may be still perturb a little bit.
Okay.
This doesn't work anymore. But in the reality, they always shift. Yeah, I believe under this stochastic market equilibrium scenario, it's not studied very much before.
Okay, good. Very
Yeah.
very interesting.
Yeah, that's right.
Okay.
This is the fundamentally different that just show static equilibrium theory is not working for uncertain market.
Uncertain market. Okay.
yeah.
Good.
Yeah. So for uncertain market, first we want to try to do is at least you do stochastic market with a certain distribution. If the uncertainty market is wild and even don't have a stationary perturbation, then that's even more challenging, right?
Okay. Okay.
That's excellent insight. Question. Yeah.
Hi, Professor.
Yeah,
Very thanks for your interesting and educated presentations topic. I'm Yiran Cui. I'm coming from engineer department, so I don't have too much math background. And my question is much related to the online marketing.
Yeah.
And my question is, for example, in my data, I study PEPs. So in PEPs, there is noise, and there maybe have some abnormals.
Yeah.
I can measure from the pressure fluctuation inside the PEP to see that there's something happen inside the PEP or not.
Yeah.
So if I do some offline case, I can first to see, or maybe you say I cluster my data and I say if they are only pure noise, or I can say there is a pure noise and there is some abnormals and then do the other things. But my question is for the second case, I don't understand is can I, for example, I only measure the pressure fluctuation inside the pipe, and I know if when the abnormal happens, the pressure fluctuation will show another feature instead of the nearly purely noise. So is that possible when I do the online? What's that word? Sorry, I forgot.
Online linear programming. What you talk about the online classification, probably. Yeah.
Yeah. So is that possible when I do the online programming? I say at first to like something to a hypothesis test to say this is the abnormal and this is not abnormal, and then learning to do the the online marketing. Is that possible?
I think there was some application to do online classification right now. So we have so if you think about the online linear programming, for each j, I needed to either set to 0 or equal to 1.
Yes.
Actually, that's the binary classification.
Okay.
Okay. So if you have some data, so you can actually use the integer to do 3 classification, to do depending on what's the value for x or whatever. So that the example I showed you, I use this cell example. The real problem is try to classify each order into 2 classes. One class x equal to 1, one class x equal to 0. You can do this by multiple class. You can still prove some nice theorem. Even this classification is online sequentially done. You could make a mistake at the beginning, but the theorem says at the end you should do accurate, more accurate, and then only error only at the beginning, and also you can bound how many errors you have. So that's what the regret represent.
Okay, so it's you mean I still need lots of data even with the abnormal
you still
case.
need a lot of data. So there was an impossibility result if your data is not enough. Even all the data presented you at the same time, you may still don't enough to do those things. Yes, so they still have a learning rate and those kind of things. Yeah.
Okay, thank you.
But it's the optimal you can do. That's the paper what I'm telling you. Very good. Yeah. It's, actually, it's become very popular, so called online classification or something, like a filtering. Yeah.
Hello, Professor. Thank you for your lecture. And I have a question about sensor network localization part. So My first question is, so what is your noise in this in your
Oh yes,
simulation?
in our experiment, yeah.
Yes, because I'm doing some related work, and because we model the noise to be Gaussian distribution. So
Yes.
In that case, we also when we do the position estimation, with the probability model, we can do the maximum likelihood estimation. So I wonder. So what is your
Yes.
your noise?
What our noise was added to the true distance, the Dij, right?
Yes.
Then we just we multiplied this by 1 plus some Gaussian variables.
Okay.
So it's like a proportion. It's like not just add absolute error to Dij. It's like a multiplicative uncertainty on Dij.
Okay. Okay.
Yeah, you can also add error to Dij and then square, or you can direct error to Dij square and then error. So this model becomes much best if you add error to Dij square. But there was a different way to do these kind of things, depending on how to construct these functions, error functions, loss function, depending on the source of the noise.
Okay, so since there's a probability model, did you try to get the Kramer-Rao lower bound with the probability?
We did not. Okay. We basically say, because we're mainly interested in, even Dij has no noise, can we still claim this is the well-behaved loss function or not?
Okay,
So
I see.
we basically, actually for this theoretical analysis, we did not add any noise. It's just in our experiment, we add some noise. The theoretical, even I know distance exactly, even I know many of those informations, this loss function still very bad functions. Still have many local minimums. Okay, this difficulty, this like a bad behavior, can only overcome by dimension expansion, whatever, which means put that SDP formulation, whatever. Yeah.
Okay, thank you. And another question is, do you have any advice to solve the conic linear program with rank constraints? Because I have difficulty when solve the problem, and so instead of solving it once, I just solve the conic linear program first, and then use the SVD to get the yes.
So my suggestion right now, to me, the best way to solve this problem is try to use matrix multiplications. So this matrix, I put them into. I use the ADMM. Seems works very well. I let this matrix to be like A times B. Okay, A only have if you want the rank to be equal to 2, this A actually is the n by 2. The B is also 2 by n. The two matrices multiplied together is n by n, but actually rank is always fixed to 2. Then I add constraints, let A equal to B. Okay?
Okay.
Then I use ADMM to solve it. Okay?
I see.
It seems works very well. This is also, of course, you can use nonlinear, but nonlinear formulation like Montero, Bureau seems also have some. But ADM seems works very well. You know what's the best? The best use SDP relaxation. Solve them roughly. Use that as an initial point. To use the first order method works very well. You don't have to solve SDP and that SDP exactly, whatever. You solve SDP relaxation. Use the project resolution into no-dimensional space. Use that as an initial point. Give to Adam or like a stochastic gradient method. actually they're always finding a very good solution. Because the SDP solution already get an initial solution very close to global minimum.
Okay. Thank you very much.
This is my suggestion.
Yeah, thank you very much.
Yeah.
So maybe we are
Yeah,
quite
sorry.
try maybe the last question if anyone has. If no, maybe we can stop here. There might be some reception outside. If anyone would like to stay for further question, probably can stay for a while.
Okay.
And we can let's thanks Professor.
Oh,
Yin.
okay. Thank you. Yeah. Thank you. Yeah.